Today we'll start with the topic radioactivity, which is again a part of SEM 4 paper 9 elements of modern physics. And today we'll start radioactivity, and the topic in short we'll discuss about the nuclear stability before moving on to radioactivity. So the nucleus of an atom, it consists of a neutron and proton, as we know, and that collectively called nucleons. And the neutron and proton reside in specific level, okay, with different binding energies. Now if a vacancy exists at lower energy level, a neutron or proton in higher energy level may fall to fill the vacancy. So this transition releases energy and gives a more stable nucleus. So the amount of energy released is related to the difference in binding energy between the higher and lower level. If a nucleus gains stability by transition of neutron between neutron energy levels or a proton between proton energy levels, the process is termed as isomeric transition. In an isomeric transition, the nucleus releases energy without a change in its number of protons or neutrons. So the initial and final energy state of the nucleus are said to be isomers. Now, a common form of isomeric transition is a gamma decay, in which the energy is released as gamma photon. An isomeric transition that completes with gamma decay is internal conversion, in which an electron from an atomic shell carries energy out of the atom. So basically, so this nuclear stability, it basically depends upon three factors. Number one is like the value of binding energy per nucleon, the value of binding energy per nucleon. Okay, higher the binding energy per nucleon, greater will be the stability. So higher the binding energy, okay, greater will be stability. Similarly, the second thing is the neutron to proton ratio. And on the third factor which will depend is the odd and even number of neutrons and protons. So this is something related to the stability of the nucleus. Now the main topic which we are talking about is the radioactivity. What is radioactivity basically is, so the phenomena of spontaneous emission of nuclear radiation, that is maybe alpha, beta, gamma, etc., by unstable nuclei is called radioactivity. Now the nuclei which shows this phenomena is called the radioactivity nuclei. The atom with radioactive nuclei are called radioactive atoms or radioactive isotopes or radioisotopes, and a material containing a large number of radioactive atoms is called either a radioactive material or a radioactive substance or radioactive source. Okay. Now, radioactivity of a sample cannot be controlled by any physical or chemical change, number one. And number two is that radioactivity is a nuclear event and not a atomic. So that has to be in our mind. So the thing again which we'll discuss is the radioactive decay law. Okay, the first thing which we will discuss over here is radioactive decay law. Okay, now this is a spontaneous radioactive decay is a spontaneous change of one nucleus to another nucleus with the emission of alpha particle or beta particle or orbital electron capture. The change in another way may be only in the energy of the nucleus which follow the emission of gamma ray. As the radioactive decay is a statistical process, okay, the exact time when a given nucleus will decay cannot be predicted. However, proportion of nuclei decaying in a certain time can be predicted very precisely. Soddy and Fagan give the following two laws for radioactive disintegration. The first law given by Soddy and Fagan for the radioactive disintegration is that the rate of radioactive disintegration, okay, at any instant t is proportional to the number of radioactive nuclei present at that instant. That is dn by dt proportional to n, where n is the number of new radioactive nuclei that have not decayed till time t. Okay, and here dn is a small fraction of this nuclei decayed during the small time interval dt. So between time t and t plus dt. So to convert the proportionality sign, we'll write dn by dt is equal to minus lambda n. Here negative sign, okay, it indicates that as time increases, the number of radioactive nuclei and decreases the time. And number 2 is the rate of radioactive disintegration depends on the nature of radioactive nuclei. Okay, so the rate of radioactive disintegration depends on the nature of radioactive nuclei. Okay, that is dn is equal to minus lambda n dt. Here lambda dt, okay, is the probability of nuclear decay with a short interval dt. Okay, so what we'll do is that we'll just write this to be equation number 1, this one to be equation number 2, and this to be equation number 3. We'll just focus on the equation 3. This equation could be written like dn by n. Now we can write equation number 3 as dn by n is equal to minus lambda dt. Integrating will get log of n is equal to minus lambda t plus some constant c. We'll integrate this particular equation. Okay, so this will be equation number 4 and this will be 5. Here c is the integration constant. Let n naught be the number of radioactive nuclei. Okay, n naught is the number of radioactive nuclei initially present. That is n is equal to n naught at t equal to 0. So we'll have ln n naught is equal to minus lambda into 0 plus c. So c is equal to lambda, you will get ln n naught. So this will be 0, so you'll get this much. Okay, so substituting this value in equation number 5, we'll get ln n is equal to minus lambda t plus ln n naught. Okay, so this equation is very similar to the expression of y is equal to mx plus c, which is the equation of a straight line. We can draw this, we can plot this on a figure. This figure can be plotted like ln n. Okay, slope of this line will be equal to minus lambda, and this is time. Okay, now this equation, this could be equation number 6. It can be written as equation number 6 can be written as ln n minus ln n naught equal to minus lambda t, or ln n by n naught equal to minus lambda t, n by n naught equal to e to the power minus lambda t, or n equal to n naught e to the power minus lambda t. Okay, so here e to the power minus lambda t, this particular time, it indicates that the radioactive nuclei decay exponentially, right? So this thing has to be kept in our mind. Okay, now the term which is associated with this is half-life. Okay, now what is half-life? Okay, now initially it is n naught. So by the time when it reaches half of the value of the initial value, say take time t subscript 1 by 2, we have from equation 3 n naught by 2 equal to n naught e to the power minus lambda t half. So half is equal to e to the power minus lambda t half, or we'll have 2 is equal to e to the power lambda t half. Okay, taking log on both sides, we'll have 2.3026 log base 10 2 equal to lambda t half into 1, or t half is equal to 2.3026 into log base 10 2 by lambda. Now this is the value of the half-life which is related with the this thing. Now substituting the value of log 2, we basically get t half is equal to 0.693 by lambda, right? Now this is something of this is like the half-life of the radioactive element. The rest of the syllabus related to the radioactive decay will continue in our second lecture. Until then, thank you.